Welcome back, folks, and the topic of today's video is going to be combustion analysis, and specifically, how do we determine the mass of oxygen in a combustion reaction if the compound that we're analyzing contains carbon, hydrogen, and oxygen. So this is the problem that we posed in class today, and we want to try to solve it because it does crop up in typical combustion kinds of problems. So to demonstrate this problem, what we want to do is work through part of 3-22 in our example problems. So in this particular case, we have a compound paracresol, which contains carbon, hydrogen, and oxygen only. And in this particular example, we're going to combust or burn 0.4039 grams of a sample of paracresol. So for the first part of this, what we want to do is to determine the percent mass of carbon, hydrogen, and oxygen in paracresol. And of course, once we have those percent masses, then you guys know how to proceed from there to calculate the empirical formula for paracresol, which I will end up leaving for you to do as an exercise. So our goal is to get percent mass of each element present in the compound. Alright, so what we have here is a combustion reaction along with some information given in the problem. So here's the combustion reaction, unbalanced. We have our paracresol, which has unknown amounts of carbon, hydrogen, and oxygen in its structure. We're going to burn it in an excess of oxygen, and we know that in any of these combustion problems involving hydrocarbons, we're going to make two products. We're going to get carbon dioxide, and we're going to get water. And of course, in a combustion analysis like this, we know that we can capture or trap the carbon dioxide and weigh it, and we can also capture and trap the water and weigh it as well. Alright, so the given in the problem is that we're starting out with a known amount of the paracresol, which we already mentioned, 0.4039 grams of it that we're going to burn. And at the end of the combustion reaction, we have trapped or isolated 1.1518 grams of carbon dioxide and 0.2694 grams of water. So we want to use this information now to get percent mass composition of the compound. Alright, so carbon and hydrogen are fairly easy to get, because as we said in class, if we combust the paracresol, there's only one place for the carbon to go. So the carbon from the compound has to go to the carbon dioxide. It's the only place for it to go. Likewise, if we're talking about the hydrogen, there's only one place for the hydrogen can go. That has to go to the water. So we know that all the hydrogen from the compound is trapped in the water. Alright? So from the masses of the CO2 and the mass of the water, we can determine the total mass of carbon and hydrogen, respectively, that came from the burned compound. Alright, so how do we do this? Well, it's again a simple mole-to-mole kind of relationship. In this case, we're going to be relating moles of the element within the compound that we're isolating. So, if we start out by getting 1.1518 grams of carbon dioxide isolated, I want to convert this first to moles of carbon dioxide, because then we can make a direct comparison between moles of carbon and moles of carbon dioxide. So, I'm going to convert carbon dioxide to moles. We get our moles of CO2, our grams of CO2 are going to cancel out. And now what I'm going to do is make a direct mole-to-mole relationship between carbon and carbon dioxide. So we can see from the formula of carbon dioxide, I have one carbon atom for every one molecule of carbon dioxide. Another way of stating this is to say that I have 1 mole of carbon atoms for every 1 mole of carbon dioxide molecules. So that's where this mole-to-mole relationship comes from. 1 carbon per CO2. Alright? So this way the moles of CO2 will cancel each other out. And now all I have to do is convert moles of carbon back to grams of carbon using the molar mass of just 1 mole of carbon atoms here. So moles of carbon will cancel with moles of carbon. And when I do this math, we will end up with 0.3143 grams of carbon. In this case, I left it to 4 sig figs because this molar mass here is to 4 sig figs. Alright, that's where I left it. So that's going to be my mass of carbon that actually came from the original compound that was burned. Likewise, I can do the very same thing for hydrogen. I can get the mass of the hydrogen by taking the mass of the H2O. I can utilize the molar mass of H2O. I know what the mass of 1 mole of H2O is. That takes me to moles of water. For moles of water, I can look again at the structure of the compound and find out how many moles of hydrogen atoms I have in 1 molecule of water. And quite obviously, for every 1 molecule of water, I've got 2 hydrogen atoms. Another way of stating that is to say that for every 1 mole of water, I've got 2 moles of hydrogen atoms. So that's where my ratio of 2 to 1 comes from with respect to hydrogen and H2O. In other words, for every 1 mole of water, I've got 2 moles of hydrogen atoms in the structure. Okay, so moles of H2O will cancel with moles of H2O. I got moles of hydrogen now. Now I can use the molar mass of hydrogen to convert that back to a mass. And when I do that, I get 0.03016 grams of hydrogen. All right, so now here's the problematic part. We've got to get to the oxygen mass. As we mentioned in class, this is problematic because we have 2 sources of oxygen here. The compound is contributing oxygen, but also the oxygen in which we're doing the combustion reaction also contributes to oxygen. And the other thing that we do is we distribute that oxygen across 2 places on the product side. We see that oxygen is present both in carbon dioxide and also in the water. So the only way now to get the mass of the oxygen is we have to do it by difference. All right? So let's find out what we know. Well, we know the original mass of the compound that we burned. Now we also know that when we burned that compound, we generated this mass of carbon. We also generated this mass of hydrogen. And the only place that carbon and hydrogen could have come from was the combustion of the compound. That carbon and that hydrogen had to come directly from the compound. All right, so if I think about this, if I have the total mass of the compound, and I've got the mass of the carbon that came from the compound, and the mass of the hydrogen that came from the compound, I ought to, by difference, be able to now determine the mass of oxygen that came specifically from the compound. All right, so we can do that. So my grams of oxygen, I wanted to set it up as an equality, are going to equal to my grams of the compound, which is the paracresol that I burned, minus the grams of carbon that I got from the compound, minus the grams of hydrogen I got from the compound. All right, so let's do that. My grams of oxygen now are equal to the original mass of the compound. That's 0.4039 grams. And that's grams of compound. Minus the grams of carbon, so that's 0.3143. That's my grams of my carbon, minus my grams of the hydrogen, 0.03016. So now that ought to give me the grams of oxygen alone. So my grams of oxygen, when I work this out mathematically, turn out to be 0.0594 to sig figs. And that's the mass of oxygen that had to come from the compound alone. All right? So now I've got masses of everything involved. So the next step that we want to make is to convert everything over to mass percent. So we'll do that in just a moment. So now, using the masses that we just calculated, we can come back and get percent masses for each one of the elements involved in the compound. So, for example, if I want to get the percent by mass of carbon, what I'm going to do is I'm going to ratio the grams of carbon in the compound to the total mass of the compound. Now remember, the total mass of the compound is the mass of the compound that we burn. So we have that. All right, so using our numbers, what we get is 0.3143 grams of carbon divided by 0.4039 grams of the compound. That's the mass that was burned. We're going to multiply it by 100% to turn it into a percent, and we get 77.82% carbon by mass. Very same thing can be done with the hydrogen mass or other hydrogen masses. What we can do is we can take the mass of the hydrogen that we got, we'll divide it by the mass of the compound, multiply by 100% now to give us a percent, and I get 7.467% hydrogen. Again, check my sig figs as we go here. All right? And finally, we can do percent oxygen. So the mass of the oxygen divided by the mass of the compound that we burned times 100%, and we get 14.7% oxygen in the compound by mass. So now that we have these numbers, you guys know what to do. We can use percents by mass to be able to then go back to empirical formula. So you have enough data now to be able to calculate the empirical formula for this particular compound, the paracresol. Now, if I also tell you that the paracresol has a molar mass of 108.1 grams per mole, you ought to be able to use that information now to calculate the actual formula of the compound. All right, so that takes care of what we want to do. We're going to do another example or two of this in class, so we'll see you next time.